Hi folks, welcome to Kinetics Notes Part 3. Get out your notes outline and let's start where we left off, which was at the topic of half-life, I believe. So, half-life of a first order or second order or zero order reaction is simply how long it takes for half of a substance to disappear, to decompose as it were. And so if what you see on the notes is a rate graph of pressure of a reactant changing over time after after about 12,000 seconds, you get to half of the original concentration, and that is the half-life. So this is sort of a nice place to come up with some shortcuts for calculating a half-life. It's a useful number, and you can always just put in the numbers and calculate, but it's nice to know a couple shortcuts. So let's talk about the shortcuts for first order and second order half-life calculations. So we're going to do some substitution of A at a certain time. So A at half-life will be equal to 0.5 of the original concentration. Mathematically, the half-life of a first-order reaction is this. If we substitute this in for the concentration at time 1/2, this is the original concentration, this is the rate constant, and this is the time. You can simplify. You can see how the concentrations of the original substance canceled out, and you can take the natural log of that 0.5 and find out that negative 0.693 is equal to the rate constant, negative rate constant times the half-life. That's a pretty easy equation. Then if you want to isolate just the half-life, you can just put the K on the other side and the negative signs like that. So an interesting point of this is that a first order process does not depend on the original concentration. It always decreases at a regular rate. That's why something that's decreasing 50% every reaction cycle is a first order reaction, like the one we saw with the Skittles. Okay, for a second order process, let's go through the same thing. If we substitute in the final concentration at 1/2, then we do a little fancy math, and you end up with 1 over the constant, the rate constant, times the original concentration equals a half-life. Okay, moving on. Let's talk about the influence of temperature on the rate of a reaction. Because remember, the temperature changes the amount of particles that have a certain amount of energy. So the reaction rate does increase as temperature increases, as you can see and you have experienced. What part of the rate expression takes this into account? What was it that you've read and you've been told changes with temperature? It's the rate constant, that K value. So let's talk about how we can actually get that K value. So it goes back to the collision model, which we have talked about a bit, but let's review. Bonds are broken and new bonds are formed in any chemical reactions, and in order to do that, they have to collide. More concentration, more collisions. They not only have to collide, but they have to collide with the correct orientation and with enough energy to cause bond breakage and formation. The activation energy is the minimum energy required to initiate a chemical reaction. Like putt-putt golf. All right, so we've looked at this reaction coordinate before, but again, let's review. This is a transition state. Up here, where you've made an activated complex that is either the combination of reaction or the change of the reactant before it's turned into the products. And the activation energy barrier that it needs to get there is this amount from the energy it started at to the energy needed for the activation state. Okay, looking at the Maxwell-Boltzmann distribution, you can see, and we have gone over this many times, that if at a given activation energy, different temperatures will give you different amounts of particles with that energy under the curve. So what you can conclude about the relationship between temperature and the fraction of molecules is that as the temperature goes up, there is a higher fraction of molecules. Well, now we could use a mathematical expression of that relationship. Here's an equation that describes that relationship. F is the fraction of molecules that can be found through the expression. And it equals e to the negative EA over RT, where EA is the activation energy, R is the gas law constant, and T is temperature in Kelvin. The gas law constant is 8.314 joules per mole Kelvin. Something you're always given, but I thought I'd put it out there for you. So we're going to use that. So Arrhenius put this into a more useful equation. He discovered that most reaction rate data obeyed an equation based on three factors: the number of collisions per time, the fraction of the collisions that had the correct orientation, and the fraction of the molecules having the activation energy. So how do you put that all together? Well, he's a bright man. He developed this equation. K, the rate constant, equals a frequency factor A times e to that number that represented the fraction of molecules that had the activation energy. Now, an easier to use version of this is to put it into the format of a linear equation. The natural log of K equals negative EA over R times 1 over T plus ln of A. All right, let's see how we can use that. So your slope, as you notice, is the negative of the activation energy over the gas law constant, with the y-intercept being ln of A. All right, so how can we use that? I'm going to rewrite the equation here so that we have it available to us. Natural log of K equals negative E activation energy over R times 1 over T plus ln of A. So if we have some data from a reaction, we have the temperatures and we have their rate constants. How can we determine the activation energy? Well, we don't know the A value, but we've got data points that we can graph. So what you need to find is, think for a second, the slope. Find the slope of the line. So for slope, you're going to need rise over run, and since your y is a natural log of K, find the change in y. Your slope is EA over R, and your x value is 1 over T. Sorry about that. So find the change in 1 over T. So let's pick a couple points. I did this myself, and I used the two most extreme points, the 773 rate constant and the 573 rate constant. One thing you need to remember is that the R value is in joules per kilogram or Kelvin mole, and that will give you a very large number. So I'm going to give you the answer in kilojoules. Take a moment, see if you can figure it out. Let's find the slope of this line. Okay, slope is 183 kilojoules per mole. When you calculated the slope directly from these numbers, you probably got 183,000. So just divide it by 1,000 to get to kilojoules. Let me know if you have any trouble, but just do rise over run. All right, now if you don't have a lot of data and you're not so certain about your points, there is a modified Arrhenius equation where you can use just 2 points, and that would be here. And it eliminates the natural log of A, so we don't have to worry about that. And you can find a ratio of the rate constants equals EA over R times 1 over T2 minus 1 over T1. Let's practice using that data, or that equation. All right, using that same decomposition reaction we just looked at, let's find the rate of decomposition of hydrogen iodide at 600 Kelvin, which is a point that's not within the data that we have. Okay, so again, I'm going to copy down the equation we're going to need for the 2-point formula, and it is ln of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. Now we're looking for K2. So let's isolate that. If you have a natural log of a fraction, you can isolate the two parts by taking natural log of K1 minus natural log of K2. This equals this. And that's going to equal EA over R times 1 over T2 minus 1 over, ignore that, T1. Let's pick a data point from the previous data. So let's go back up. Okay, ignore the writing. Let's take the 573 value. The rate constant is 2.91 times 10 to the negative 6. Okay. So if our ln of K1 is ln of 2.91 times 10 to the negative 6 minus ln of K2 equals our EA. Now we have to match the units in EA and R, so I'm just going to put down 187,000 joules per mole divided by 8.314 joules per mole Kelvin times 1 over our 600 minus 1 over 573. Okay, do your magic math, and the answer should come out to be 1.69 times 10 to the negative 5th molarity per second. And if you go back and look at the data that we have, that fits nicely in between the two values that surround it. Okay, that is enough for today. Good luck with the problems, and I'll see you in class the next time. Bye.